Approximation to areas. Okay, integration is terrific to find areas under these unusual curves and things like that. But it relies us on being able to integrate the function. Now, certainly at this stage, with what we know, pretty much we're restricted to polynomials at the moment. I mean, we'll see other functions as we go along during the course, but even then, there are some functions which we just can't integrate. We don't know how yet. So we have to have some sort of method to approximate better than using rectangles. Because I mean, rectangles gave us, quite a bad estimate until we got several rectangles. So the first one we look at is the trapezoidal rule. The Americans call trapeziums trapezoids, but we adopt the name trapezoidal rule because trapezoidal rule is very hard to say. So trapezoidal rule, and it makes sense when you think about it. Instead of creating a rectangle, why don't we just join the 2 points up and create a trapezium? And clearly, that's going to be a better estimate than using a rectangle. Okay. And of course, the formula for a trapezium, half perpendicular height, which in this case would be b minus a, and then the length of the parallel side, so whatever function a is plus whatever function b is. But of course, just like we saw with the rectangles, if we, instead of using one trapezium, I use 2 trapeziums, I'll get a better estimate. So let's put it in C, which will be in the middle of A and B, and we can see that the gap is smaller than the one over there straight away. So if I added up these 2 trapeziums, the first one would have a height of C minus A, the second one B minus C. But if I've chosen C to be in the middle, then C minus A and B minus C is going to be the same. So I could factorise this. I just chose to make it C minus A. And I'd end up with function A, 2 lots of function C, and function B. Okay. Well, let's split it into 3 trapeziums. Ooh, look how little the gap is now. And so there's the formula for my 3 trapeziums. But once again, I've chosen C and D so that they're nicely evenly spaced. So C minus A is the same as D minus C is the same as B minus D. And again, I could factorise, and I start noticing a pattern. I'm always going to get 1 times the end ones, because they're only included in 1 trapezium, but it'll be twice all the ones in the middle, because they'll always be involved in 2 trapeziums. So a formula, the way I write it, well, the exact area would be the integral, of course. If we could find it, that'd be terrific. Otherwise, and that's how I write my formula, h on 2, where h is the height of the trapezium, y naught and yn are the end ones, and then just 2y, the others. Right? Technical term there, others. Okay. The reason I start with y naught instead of y1 is so that I finish up with yn, which will match the number of trapeziums I have. Some people start with 1 and end up with n plus 1. It's the same formula. It doesn't really matter. And so to work out the height of the trapeziums, well, we'd go b minus a, and we'd divide it by however many trapeziums we want to use. Now, keep in mind, you'll always end up with 1 more function value than you do the number of trapeziums, because each trapezium has 2 function values involved, and so we'll end up with 1 more. Let's have a look at an example. Now, I've chosen a curve that, okay, at this stage, we can't integrate, but we do know how to find the exact value, because 4 minus x squared to the power of half is, of course, a semicircle. Yeah, it's a semicircle. And we're going between 0 and 2, so I'll actually have a quarter of a circle. So I can work out the exact value so we can compare how good our estimate is. All right, we're going between 0 and 2 for intervals. Sometimes they'll use the term intervals, sometimes they'll use the term strips, sometimes they'll say sub-intervals, sometimes they'll say trapeziums. It all means the same thing. 4 of them we're going to have. So b minus a over 4, I know there's going to be a half between each of my intervals. So I draw up a table of values. So I know I'm going up by halves, start at 0, then 0.5, 1, 1.52. Substitute into my formula, 4 minus x squared to the power of a half. Now notice, the answer they set to 3 decimal places. So in my table of value, I always carry one more. So it's to try and avoid rounding errors. If I was to round them all to 3 decimal places at this stage, then each, say one's rounded up, and then the next one's rounded up, and then the next one's rounded up, and I add them all together, I might get a little bit more than I actually need. So I always carry one extra. There's my formula. H on 2, Y naught, 2Y others, YN. But what I do to remind myself is above the table of values, I say, okay, I know the end ones are times 1, and the middle ones are times 2. So that just keeps me in check. Which ones am I multiplying by what? So let's substitute in. H was 0.5 over 2, and then 2 and 0 were the end ones. 2 times all the ones in the middle. Bit of calculator work, and then I've rounded it off to 3 decimal places. 2.996. Quarter of a circle. I conveniently picked one because the radius there works out to be pi. So we know it should be 3.1415. 9, 2, 6, 5, 3, 5, 8, 9, 7, 9, 3, 2, 3, 8, 4, 6, 2, 6, 4, 3, 3, 8, 3, 2, 7, 9, 5, 0, 2, 8, 8, 4, 1, 9, 7, 1, 6, 9, 3, 9, 9, 3, 7, 5, 1, 0, 5, 8, 2, 0, 9, 7, 4, 9, 4, 4, 5, 9, 2, 3, 0, 7, 8, 1, 6, 4, 0, 6, 2, 8. Approximately. Percentage error. So the difference between the two, divided by the actual result, times by 100 to turn it into a percentage, and we've got about a 4.6% error in that measurement. So that's our trapezoidal rule. But there's a better one. Simpson's rule. All right, so again, the exact area. This time there's our formula. H on 3, it's still 1 times the end ones, but now in the middle we alternate. And I say odd and even, because if I've made the first one Y0, my next one would be Y1, then Y2, Y3. So Y1, Y3, Y5, and so on would be what I'm talking about with the odd ones. And then Y2, Y4, Y6 would be the even ones. But basically it starts with 4 and it alternates. 4, 2, 4, 2, and so on. What it uses is actually parabolas. So it's using a curve to estimate a curve. And so one will be concave up, one will be concave down, and they overlap 2 of the intervals to come up with this estimate. So B minus A on N is still the same. Let's do the exact same question. There's my table of values. There's my formula, 4y odd, 2y even. But again, this is where I guess writing it above the table is really useful. So I make sure I know which ones am I multiplying by 4, which ones am I multiplying by 2. So I start off with 4, and then there's 2. It should be symmetric. Simpson rule works great when you've got that symmetry. If you have one more function value, then you wouldn't have the symmetry, because in the middle you'd go 4, 2, 4, 2. It's not symmetric anymore, and it's not as good. It works a lot better when you have that nice symmetry to it. So substituting into that one, so 4 times, and this one's Y1, so I'd consider that an odd one. I'm not saying 1.9365 is an odd number, but clearly it's not. But that's Y1 and Y3, and then Y2 in the middle. 3.084. Remember the exact value is pi, so it is a better approximation. That one works out to be about a 1.8% error. Of course, what should happen is if you use Simpson's rule to estimate the area under a parabola, you should get an exact value, because you're using a parabola to estimate the area under a parabola. So it should come out very neat indeed. So basically it's using curves to estimate curves rather than using straight lines to estimate curves. Exclaim! Alternative working out. I saw this in a solution once, a different way of setting it out. So here's our trapezoidal rule. And they say, oh, well, the area is that. So they didn't actually have a formula, But if you have a look at it, it's the same thing. On the top of the fraction is exactly what I had inside the parentheses. So the end one's times 1, 2 times in the middle. But on the bottom of the fraction, it just repeated that pattern I've written on the top of the table. 1, 2, 2, 1. And then we multiply it by 2 minus 0, because we're going from 2 to 0. And trust me, that does work out to be exactly the same thing. 2.996. I thought that was quite neat. And I wanted to see if I could use the same thing for Simpson's rule. Turns out it works for Simpson's rule as well. If we did Simpson's rule, there's our table. So same idea. On the top of the fraction, exactly what I would have had in the middle of the parentheses there. So 2 plus 4 lots and so on. On the bottom, there's the pattern. 1, 4, 2, 4, 1. And then multiply by how wide we're going. So 2 minus 0. And again, it comes out to be the same thing. So it's an alternative way of writing it out. Okay, so there we go. 11i is trapezoidal rule. We'll do the odds. And because we like a bit of variety, 11j, we'll do the evens.